our first speaker is Adam Pajonk. Adam is a PhD researcher at TU Delft and Münster School of Architecture. His research is on multi-material additive manufacturing in architecture and construction. He holds a master in architecture from Münster School of Architecture. He's been collaborating in different projects and been teaching at Münster School of Architecture. Also been planning and implementing a Marathon event at Münster in collaboration with Covestro. And since 2016, he's been inventing and researching on the informed printing process with company Covestro. So today he will be presenting a structured material by additive manufacturing. Adam, I will leave the screen to you. Okay, great.
Okay, so thank you very much for the introduction. And can you hear me loud and clear?
Yes.
Perfectly. So yeah, very great to be here, and thank you very much for the invitation for this great symposium. So today I'm going to basically present the current state of research, which is basically on my PhD research on multi-material additive manufacturing in architecture and construction, which I do at the TU Delft as well as at the Münster School of Architecture. I will start with a bit of background on the work, and which to some extent led to this here presented printing approach. So in 2016, we developed a method which is called informed printing together with the company Covestro, which basically is a chemical company and provides polyurethane material as well as polycarbonate. So informed printing is a manufacturing approach which allows to alter the compression behavior of soft foam by simply injecting rigid structure into the foam. And so by basically defining the structure and injecting a specific structure, we could, as with this example, initiate a torsional movement by simply using twisted rods, a twisted rod structure into the foam. And this basically allows us to go basically beyond the properties of the foam itself and start to basically design the way such a material starts to behave under compression. And with this idea and throughout the research project, we basically developed a whole catalog of different structures and corresponding functions basically with this process. Now, moving over to the construction and architectural scale and to the actual PhD research project. With this approach in mind, we thought about how can we basically implement a similar way of fabricating objects in the construction industry, and particularly on the building envelope. So maybe to the motivation of this research, while we can see a number of 3D printed buildings and research on this topic, we still see that the way of how building components, and especially facade components such as windows or window frames or individual layer of a building envelope are installed and connected to the building structure, remain largely conventional. So mainly they are still done manually on the construction side. And the problem here is, while construction is known for basically an almost stagnating increase in productivity growth compared to manufacturing and total economy, on-site execution particularly has been identified as one of the main root causes for this low productivity. And with these go a number of different problems, such as, for instance, frequent misunderstandings due to poor communication and transition from planning to construction, building defects, as well as errors correlated to humans. This issue is actually even further propelled by a rising lack of skilled workforces, which poses additional pressure on the construction activities, as well as the high risk of occupational diseases and accidents on the construction side. Now, we looked into additive manufacturing on a larger scale and sort of tried to review the current state of art and identified that while a couple of projects do appear actually since a decade, starting probably at the MIT, we still see that for one, there is a large focus also in regard to the maturity on concrete material. So we can see that there are some approaches, but they focus on concrete, while especially polymer materials are rather rare. So we identified here a gap for suitable processes which can be applied in construction and sort of go beyond concrete materials and therefore the building structure itself. Now, with this in mind, we started to look into 3D printing with reactive polymers, particularly polyurethane. And well, this approach is not completely new. And in construction scale additive manufacturing, the use of reactive polymer is probably mostly known through large scale foam structures, where the extruded foam is usually used as a stay-in-place formwork, which then simultaneously provides insulation capabilities for the pure concrete wall. However, we looked at this material not as a form of 3D printed construction foam, but rather as a material which allows a wide variety of properties, which goes beyond these of a foam and can be obtained basically. So with this process, what you basically do is you have a two-component system where you, while extruding it, basically mix both components and right before the extrusion. And after extrusion, the material starts to react and very quickly harden. So as a first step, we basically created the setup which is based on a robot arm and this extrusion unit, which gives us basically a lot of freedom in terms of orientation, as well as size of these printed objects. And so with this setup, we started basically to first identify the inherent possibilities and constraints of this approach, such as basically being able to print vertically on top of a surface. And on the topic of printing basically on top of the surface, polyurethane also provides strong adhesion. So we tested basically printing directly on top of an object, such as these concrete elements. And we even looked a little bit further into this and conducted an adhesive tensile test. And with this test, we basically achieved an average of 1.63 Newton per square millimeter of tensile strength. Or to put it in another way, we could basically hang 326 kilogram of load on one of these testing stamps, which has a diameter of 50 millimeters. So while we found a lot of ways to improve this even further. However, this gave us an initial idea of what this process is basically capable of and opened up the possibilities, basically the possibility to not only create components, which after printing have to be installed on the construction site, but could also be basically printed directly on the construction site. So now coming back to the initial idea of kind of enabling multi-property printing, we started basically to refine this process by not only implementing the two components that are needed to kind of create this polyurethane, but kind of adding more components, which then could kind of throughout the print be switched between different sections of the printed objects. So as you can see, for instance, you could kind of just change from one mixture to another throughout the print of a single layer. And now, while first initial tests were done with just different colored materials, we then looked into a set of specific material properties which could be combined and used for further testing. So we basically defined a hard compound, a soft compound, and in addition to this, also a compound which kind of represents a rather very low density compound, which is in this case created with hollow glass microspheres. And while polyurethane has the ability to create a foam with a very low density just by using a foaming agent, tests that we conducted kind of lead to several problems with this. Specifically, the process of forming itself is rather difficult to control, and especially to use if the intention is to create a rather accurate object. So therefore, we decided to, for this moment, stick with these hollow glass microspheres as an additive. And so these properties were then implemented in an additive manufacturing process. However, with this change, a number of different problems kind of occurred, such as having to handle different mixing ratios for the respective material properties, and kind of to adjust and combine them with the printing process itself. So here you can see the whole setup of this process, where we have basically the mixing unit attached to the robot arm, and a number of different materials which are then combined throughout the printing. So moving on, after basically defining these possible properties of the setup, we looked into ways of applying basically multi-property 3D printing. And here we basically start to describe two different scales on which properties can be implemented. First, on a large scale, where we basically operate at the level of the overall form of a component and actually assign different material properties rather to whole areas or sections of the 3D printed component. Such as, for instance, with this implemented movable joints, where we can kind of create this moving without any form of assembling or whatsoever, but just by basically changing the composition of or polyurethane material. Or similarly, with these material properties can also be kind of put on more filigrane structures, where basically one part of the structure is rather rigid, while the other part is created with this softer compound. And in contrast to this, small scale applications, which operate at the level of the material structure itself. So basically the infrastructure of the 3D printed component, and rather starting to define the printed path in respect to the material properties. So here we basically developed in a first step a number of different structures, and this approach basically leads to a higher differentiation of the material properties to the volume of the printed objects, and ultimately allow us to design, in this case, the material behavior. That again, and similarly to the very first project, the informed printing project that I saw. In this case, we kind of achieve properties that go beyond basically just the properties of the materials itself. As for instance, with this example, where we can kind of define this vertical movement, which is sort of controlled by the softer material compound. However, horizontal movement is restricted by basically this interlocking structure, or by basically creating a suspended connection, which is created with this softer compound between different parts of the structure. Or even enabling rotational movement, while at the same time restricting it to a certain extent through the ductile material. Now, another way to look at this is basically to first define a lattice structure, and then basically apply these different material properties on a small scale to this predefined structure. And now, what we first did was basically kind of look for a suitable structure. So the structure itself has to be basically designed in a way that it sort of allows not only movement in the horizontal direction, but also in the vertical. So therefore, we had basically to kind of introduce this sort of shift between these layers. And in addition to this, we also had to look at the printing process itself very closely. So while this structure itself is very much defined by bridging between different layers, we first had to kind of identify what is basically the amount of bridging that we can kind of achieve with this process. And in addition to this, also, we had basically to make sure that the whole structure itself is not starting to sink or collapse, which is mainly linked to the way of how these individual layers kind of sink after printing. And in order to kind of handle this, you have to have a specific amount of layers until basically the very top layer is again completely flat. So in this case, we just had to introduce basically for each layer of this lattice structure a number of layers. And now with these parameters, we basically started to create basically the boundaries of the structure with the maximum of rigidity on the left side and with the hard compound, and on the right side the maximum of ductility or with the soft compound. And now with these extremes in mind, we wondered what's in between these, and we basically looked at possibilities to define the structure in order to kind of achieve something which is rather completely stiff nor completely flexible. So therefore, we basically just started to pick individual lines within this structure and sort of assign different material properties to these, which then ultimately leads to basically a structure which kind of keeps a lot of flexibility, while it kind of also restricts the movement along the blue rods of the structure. So finishing the presentation, outlook on a potential future application and what we kind of intend with this approach. So the idea behind this approach is basically to integrate the complexity of connections which are in the building envelope by basically integrating the functions the connection have to fulfill into the 3D printed component itself. And as we see, for example, with the typical window frame, where the frame itself not only has to transfer loads from self-weight and push and pull forces, but also has to basically absorb and make sure the movement of the building components and from material angle elongation are handled properly. And in addition to this, the connection itself would also kind of compensate for inaccuracies, water and airtight, make sure that we create a water and airtight connection, which can handle movements, as well as reduce transmission, heat loss, ensure a minimum surface temperature, as well as make sure that we have a sound insulation through the decoupling of the components itself. So the idea is basically to kind of combine all of these functions in a 3D printed frame structure, which can ideally be directly applied on the construction site itself. And so with this presentation, we basically described the possible fabrication approach for creating these types of components, which not only allow to reduce the need for assembly to the use of multi-material or multi-properties, but also introduce and extend the ability of how we can kind of apply 3D printing by using it as a form of printing on top of a building structure, and therefore basically eliminating the act of manual installation processes on the construction side. So this is basically the point where we are right now with this research, and we are basically very excited to kind of move on and start to develop concrete applications with this. So thank you very much for your attention, and yeah, I'm looking very forward for questions.
Thank you, Adam. Oliver, you want to start with a question, or should I?
I could start with a question. Adam, thank you very much for this super interesting presentation, and also for showing us ongoing research. That's how I understood you, right? You're right in the middle of something here. What I understand is that you design material behavior. If you look at if you look at metamaterials, something that I'm sure you looked at, there's this blurring between designing the material or designing the structure that creates a certain behavior. Now you showed us the layering of grid or lattice structures, which are quite unified. So my question would be, in your next step of the research, would you aim for controlling material behavior also through kind of micro geometry, like Panayotis Michalatos once said, architects might become designers of the material, so they don't design in 1 to 100, but maybe in 1,000 to 1, because they really design the tiny structures of a material. What are your goals here?
Yeah, exactly. So maybe what we think is that we kind of add another layer to this approach, where we not only are able to kind of define the material structure and thereby control the behavior, but also kind of introduce different material properties, which therefore kind of enlarges basically the range of what we can achieve with this approach. And so I totally agree with this approach of now we are starting basically to design basically from the scale of the material itself to the larger scale of architecture. So yeah, and with the lattice structure, this was basically just used as a very simple form. And now, I mean, the problem here is there are so many different parameters that we can look at and start to explore. And actually, this is basically the exciting part, because we can now start really just to think about everything possible and basically just print it and look at it and examine it and see what we can actually achieve. Because to some extent, and this was especially in the very first project that I showed, the case is we can kind of think about what we try to achieve, but there's always this element of surprise where we kind of realize that now we have something achieved that we didn't really thought about. And therefore,
do we need new design tools or new forms of design representations for that to explore what's possible?
I mean, yeah, this is very, very closely linked to the way of manufacturing and basically implementing this in the design process itself. Because at this point, you really design every single part of the 3D print. And actually, you have to design it, right? It does depend on which scale you are basically working. This kind of forms the tool you are using, while the larger scale that I showed rather is based on simply kind of defining larger areas of the component and just setting the material properties to them. While the second approach, this small scale approach, really is based on defining each individual printing part. And this absolutely needs a new way basically of designing, where you kind of design from the ground up from the fabrication process itself.
Thank you.
Thank you, Adam. It's a beautiful project. I do have some very, very much questions, but I think we should go on with the next speaker if we want to keep up with the schedule. Just wanted to add before I go to that, I thought it was amazing the position you picked or the place you picked for the project, where it's in between two different dynamic forces and mediating these two different movement in the building. So it seems fitting very well, but I'm also very interested on what Oliver asked in terms of design tools, and especially on how the materiality will be integrated into the overall form, if it's only through height, or you would be able at some point to actually inject different material as you print. Obviously, that's kind of a constraint of printing to immediately switch between material within one layer.